session. Radha Jagadeesan from DePaul University will talk about, eventually we'll talk about linearizability, eventual consistency. And here's Radha.
Thanks for having me. Yeah, thanks for the invitation. So the context of this talk is the correctness of distributed algorithms, and this is joint work with my colleague James Riley. Let's see. Okay, so how am I going to go about this talk? So I'll spend quite a bit of time just talking about the context of the problem. This is distributed data structures. We will look at some simple implementations. And the particular problem we'll be addressing is in what sense are these data structures correct? And the ideas of compositionality and the related idea of abstraction are going to play a key role in how the correctness definition comes out. And for most of the talk, I'm going to eschew formal definitions and asking for your trust, but if you do not, or in any case, there's a tech report. Okay, so. All right, so let's set up some notation so that we can work. So let's think of as just a simple thing like an integer set. Most of the time, you're just going to have a binary set, so we have sets just with 0 and 1, perhaps. We'll write plus 0 for adding 0 to the set and minus 0 for removing the set. And these methods are not going to return anything. And then we're going to have ways to query the set. And when we query the set, we're going to get back a Boolean. So I can query if 1 is present. And if 1 is present, I indicate that with a check. And if 1 is not present, the false answer I indicate with an X. And
are these sets or multi-sets?
Sets.
So if you add 0 twice,
you will be just 1. Yeah. I'm hesitating because there is going to be some subtlety in that answer in the data structures we look at. But the intention is that at the level of the sequential spec, we are really thinking of sets with idempotency, with an idempotent addition. Yeah?
If you could try to repeat when the questions come.
Yeah. So these are going to be sets. The intention is these are going to be sets, not multi-sets. So adding 0 twice is the same as adding 0 once. Okay. And we want to think of this data structure via its valid permitted traces. Let's think about so when we start off, there's nothing in the set. So of course, we're going to get false for 0. Then we add 0. Then we ask for 0. Yeah, 0 is there, but still 1 is not there. Okay, so that's a typical trace we have. And here we have a 0. We add a 0, add a 1. We ask for a 0. Of course, we're going to find it. We ask for a 1. We're going to find it. Then when we remove the 1, the 0 is still there, but the 1 is not. Okay, so we're thinking of a data structure as being specified completely by the traces it permits. Okay, so that's what we're doing. But what we want to do is we want to look at distributed implementations of sets. Okay, so here is a simple example. So here the idea is I have the set, it's going to be replicated. So the 2 lines there indicate 2 different replicas. They're running separately. Why we want to do this, we will discuss momentarily. And let's consider a particular interaction with this replicated data structure. On the top replica, we're going to add a 0, check for the 0, and then check for a 1 a couple of times. And on the bottom replica, we're going to add a 1 and check for the 1 and check for 0 twice. Okay? And we're going to be aggressive in doing the accessors. What do I mean by that? So I add the 0, ask for the 0, I'm going to find it. Yeah, so the 0 is going to be there. Now, of course, the 1 has happened somewhere else. So the upper replica still doesn't know whether this has happened. But the answer is still going to be aggressive. It's going to say, well, I don't know a 1 right now. So that's why we have the 1, which is a false. And when the other replica does update it, then I come to know that I have a 1. So at the end, I end up with a 1 here too. okay? And that should have been a 0. That's a typo, okay? So, but when all the messages have flown around and the system has quiesced, we end up with both sides telling us that we have a 0 and we have a 1, yeah? This is a distributed system, so where do you get order from? You get order in a couple of different ways. One, in the course of a replica, as a replica evolves, you get order. And the second place where you get order is when you receive messages. Yeah? So for example, it's here, right? I'm receiving a message of the update of 1. And often it's useful just to think of the underlying partial order. Okay? And really, even though I'll be drawing lots of diagrams like that, the definitions are really working at the level of the partial order. The structure of the replicas itself is not important. What is important is the structure of the partial order. Okay. So now, why are we doing this? Why do well? So because, well, we don't want to synchronize these replicas aggressively because serialization affects the performance. It affects how scalable these things are. And also there is the cap theorem, so we can't have all these three properties simultaneously, so we can't have consistency where every read receives the most recent writes, availability where every request receives a response, and where the system works despite partition tolerance. So we can't have all three simultaneously. So what is done in modern distributed systems is typically a liberalization of the notion of consistency. Okay, and we are going to explore what's going to happen in our data structures. Okay, so let's look at a couple of examples. Okay, so this is the sort of the framework of convergent and commutative replicated data types. We are still working with sets, and when we are adding zeros and ones, clearly those operations commute. Okay, what do we do when we have operations which do not commute? Okay, so for example, when I have a removal of a 0 and an addition of a 0, okay, then each algorithm resolves these conflicts differently. The observed remove set resolves it by saying that the remove only removes the adds which it has seen. Okay, so what does that mean? So in order to understand that, let's think of this evolution here. This is a possible evolution following this algorithm. Now let's look at the third replica. It gets an update of the add of the 0. It gets an update of the another add of the 0. It's going to say, yes, I have a 0. Then it gets an update of the remove of the 0. Okay, and yet it's going to say, yes, I still have a 0. And why is that? That's because the removal does not remove the add which it has not seen. Okay, that's why it's called observed remove. The remove only removes the adds it has seen. Or to think of it purely in terms of the partial order, what we, here, if you have a remove and an add which is concurrent with it, there's no order, then the add wins. Okay, so to put it all together, the set trace which validates that execution, so to speak, in some informal sense, is where you have a +0 and a -0 corresponding to that, and then the +0 coming from here. And the sense in which the +0 wins is that, it wins over the -0 with which it is concurrent. Okay? And just to give you one more example quickly before we launch in, just to say, because I'm going to be doing sets all along, but it's not to do with the subtleties of sets. So here's an example of distributed text editors. I'm going to run through this somewhat quickly. So I initialize, so here you think of A, B, and C as letters. Let's just simplify matters a bit. Let's assume that we only add characters once. Okay, so I will not add B twice. That's not essential to the algorithm, but it just makes our view of it simpler. So here, let me start with a piece of text. I initialize it with C. And then in one replica, someone adds a B before the C. In another replica, someone adds a B before us, and another replica, someone adds a D after the C. So when we query, we'll see B, C, D. Okay, when everything has happened. But now here's some interesting thing that happens. In one replica, one person removes the D, but adds an A before the B. Okay, and symmetrically in the other replica, one removes the B, but adds an E after the D. Okay, and now one can ask, hey, what is the state of the document at this point? Okay, one consistent view to take is to take that I'll be left with A, C, E. That is to say, A is before the B, hence before the C. E is after the D, hence after the C. Okay, and there is a sequential trace which validates it. And if you look at the sequential trace which validates it, we notice that it is going to move the removal of D, which is concurrent with the operation on D, after the D, right? The removals come after. In this sense, the choice made in this algorithm is symmetric to the choice made in the OR set algorithm. Here, the deletion wins. Okay, so this is these are sort of two examples to kind of keep in mind. And just we can, the OR set looks seemingly simple, but you can build pretty complicated pictures. And maybe I should just talk a little bit about this. So I have an addition of 0, and then I add and remove the 1. Here I have add 1, and I add and remove the 0. Yeah. And the OR set, well, we expect to see both elements present. Why is that? Because I have a 0, which is concurrent, add 0, which is concurrent with the remove, so I'm going to get that. I have add 1, which is concurrent with that, so I expect to see that. Okay, so there are a lot of subtle things that happen in these algorithms. Yeah. On the other hand, this is still a set in some deep sense. Yeah. So, for example, these are behaviors which the OR set does not create. Okay, and this would be atrocious, right? Because we see the 1 and then we remove it for no reason. Okay, or we say a 0 is present without any evidence for it. Right? Or perhaps even more subtly, we have an add and a remove, and the order between them is resolved differently in different parts of the distributed system. Okay, these do not happen in the OR set. Okay, so the question we are going to ask is, well, when does an OR set implement a set? Okay, and what are the constraints? Okay, and what are we going to say? So we want some basic constraints on our definition. We want a definition to support some notion of compositionality. Here I've written a really simple example. So let's say we have two independent sets, and now I just I have two implementations of them. They don't interact with each other. And all that I want to say is, well, if I run the two implementations side by side, I'm going to get an implementation of a double set. Yeah, and this is called compositionality in this literature, Hurley and Weng. There's a different flavor of compositionality one can ask, and in this literature it's called abstraction, and explored by these authors in the concurrent context. So let's say we have a graph, and to implement a graph, I need a set of vertices and a set of edges. Okay, and now what do I want to do? So I program the graph against the interface of the sets. Okay, so I do not know about the implementations. Now what I want to know is, if when programming against the interface I have a correct graph, then that should still be correct if I substitute in the actual implementations, right? So this is sort of if one thought of the previous slide as being horizontal in some sense, this is vertical. This is refinement. Yeah, you're replacing the interface by the implementation. Okay, so we want our definition, whatever it might be, to satisfy these properties. Also, we want it to be consistent with the single-threaded world. If I just have one replica, it must look like a normal set. If I have only one place where my updates are happening, so our social networks used to be implemented like this. All the updates only happened in California, and the only thing we saw on our phones was the reads. Okay, we were only doing reads on the phone. If we had such a system, then any execution of a system correct in my sense should automatically be linearizable. Okay, and there's no need to read this. Just think of this as saying the distributed implementation should not expose new intermediate states. Okay, that's what we want. And the reason there's some historical context to this constraint, there are implementations out there which violate this constraint. Okay, so people discovered this after the fact. Okay, so these are the things we want. Okay, and so what is our first choice? We revisit something which is done in in traditional concurrency. Yeah. So this is the world of linearizability. I'm just drawing an automaton here, okay? And the idea is, in a concurrent world, an implementation is good if all the executions are accepted by this automaton. Okay, so what does this automaton have? The states are going to be labeled by sequences of methods. And the invariant we'll maintain is that as we go from one state to another, we will always have proper extensions. Okay, so if I have an edge from there to there, that had better be a prefix. Okay, and what are the things on the edges? The things on the edges are palm sets. Okay, so what does that mean? So let's come here. So I start here, nothing has happened. I add a 0, so I just have a 0. In this case, it's really simple. Again, here I add a 1, I have a 1. Or I could have a 0 and a 1 happen simultaneously. And here, of course, you have two possible choices. Either it is 0, 1 or 1, 0. It doesn't matter. I'm only showing 1 here. But let's look at some interesting thing happen here. Now here we see a real palm set in action. So here, what I want to do is I want to say, hey, can I accept a check 1 and a check 0? But I want to give some extra information about the check 1, which is its history. Okay, so the new events are just the things at the fringe of the palm set, which is the check 1 and the check 0. But I want to say the check 1 is after the plus 0, and the check 0 is after the plus 1, which means that the only place where I could stick them in is at the end. Okay, so what I have is basically sequences of labels, and the transitions are palm sets, and the resulting state has to be consistent. Really a suffix or proper extension of the starting state and of the palm set.
When you read that vertical bar, does it mean everything on the left is independent of everything on the right?
Oh no, that's just parallel. I mean, two things happening concurrently. I'm just a notation for a palm set.
Right, but the check 1 could happen before the plus 1?
Yeah. This is totally concurrent. Okay, so the way to read this palm set is. It's a check 1 which is independent from a check 0. It could happen either order. Yeah, so there is another order possible here. But the check 1 has to be after the plus 0.
But what about the plus 1?
No constraints. No constraints. Yeah. No constraints. Yeah. Right. Except that the only way to get a check 1 is after the plus 1. That's why it's forced there. Yeah. Right. So this is 0. So this is our so this is the model for concurrency. So you say a concurrent implementation is good if it is simulated by this automaton. This is from Hurley and Wing. Yeah, but this world is too restricted for us. Okay, it's too restricted for us. Let's go back to the simple example. We don't have a way to linearize this. Yeah, so basically, think of how are we going to place x1 and x0 here. We just don't have a good place to put it there. Okay, because we want to put the x0, but the x0 has to be after the plus 1, so it's got to come here. That's not possible. So we need something a little more looser. Okay. So what's the idea? The idea in the literature is to think of, hey, let's think of a different model. And the intuitive idea is that the states converge when all the messages have been delivered. So when everything is delivered, we are in a state with 0 and 1. And this loose idea is called eventual consistency. And for some kinds of applications, this is fine. But but from a programming language perspective, this is just not good enough, because it doesn't tell us anything when there are messages still out there in the network. Right? So we have a problem. So for example, here there's a message waiting in the network. So in principle, the definition allows me all sorts of silly stuff. Here again, there are messages out in the network, so it doesn't check the inconsistency you see in the diagram below. Okay? Or more generally, what is happening? We talked about our earlier constraints. We wanted to satisfy constraints A, B, C. This definition which just imposes this does not give us enough properties of the implementations which satisfy them. Okay. So what are we going to do? Oh, all right. So there's some prior work, some of which I was involved in. They go along two routes. One route is to say we'll abandon sequential specifications. Okay. And that has the advantage that it's able to rationally speak about all the implementations out there. Or there is the other version which takes the spec seriously, but which is not good enough to handle all the implementations out there. Okay? So what we want to do is we want to try to be a little bit more, right? So what I want to do in the next few minutes is give you an idea of the basic ingredients, okay? And I'm going to do this mostly with pictures and all right, so let's see. So basically there are going to be two ideas, and just let's keep that in mind. One is to sort of be more extensional in a certain sense. And the second is to take the idea that time in a distributed system is not linear. It's, you can't have a global time. At some deep level, it's a partial order. So we're going to try to incorporate that into our definition. Okay. So, right. So first, let's. What do I mean by this? We want to be a little bit more extensional. Okay. So in the linearizability state machine, right? We just have sequences of labels. We do not worry about whether some of these states are really bisimilar to the other states. Yeah, I mean, in some intuitive sense. Like for example, let's think about that state and that state. Okay, so I have +0 there, and I have here all that I've done is I have an accessor for 1 which is not there, and we know intuitively that these two states are bisimilar. The only difference between the evolution from here and here is going to be sticking in the extra accessor there. That's a really simple example. Yeah, and there is a version of linearizability which does take this into account. It's in the database literature. It's called conflict serializability, but we have to go a little bit further. So let's do it. Full hog, right? So we'll follow some, what I've done basically here, for those in the know, is I'm going to adopt an old idea from a paper of Steve Brookes, but adapted here. So what is the idea? So we're going to take sequences and we're going to identify them, okay? When are we going to identify them? Well, when they give you the same sequences of states, up to repetition of states, okay? So another way of thinking about it is just to say, oh, I don't have any new intermediate states, okay? So what does that mean? So for example, here, if I add 0 twice, here the sequence of states is, well, whatever you start here, 0 present here. Here, whatever you start here and 0 present. So really, all that has happened is we have stuttered the 0 present state twice. Okay, this is stuttering. Or the same thing happens even when we just have an accessor. Okay, so what are we going to do? What we're going to do is we're going to identify these states. And so if we do this analysis a little bit in our head, we realize that the equivalence classes for a set over one element is going to be basically the canonical elements are just given by the alternations between plus and minus. It doesn't matter how many minuses you have there, okay? So you can draw this diagram out. Yeah, you can draw this diagram out. I shouldn't hassle you too much about it because I'm going to hassle you a bit now, momentarily. So, okay, so this kind of gives you a sense for what this means, okay? Now the next thing we do is we're going to take time seriously, okay? So we'll explore this in two different ways. The first is that what we notice in the linearizability automaton is that there's a very strict prefix ordering, as I said earlier. As we walk down, we are sort of adding up stuff. Okay, we never lose anything, and it's always going forward. Okay. Now what we're going to do is, in a distributed system, time works differently, right? So when I receive messages, it may not be message, when I add message, it may be messages which have happened concurrently to me. Okay, so we are going to accommodate that. And the way we are going to accommodate that is that now my transitions may not just be between prefixes, it may be to subsequences. So let me explain that, okay? So let's go back here. This is where I start. I remove, I'm going to be there. When I add, I'm going to be there, okay? Let's look at the part which looks like linearizability. So here, I get a remove, I add it, okay? It's afterwards. Or I get a remove with a history, I still go there. This is just like it used to be. We also have another option, which is when I get a remove, it could be a remove which is happening concurrently. So in fact, it's put in before, okay? So the portion of the diagram here, which wasn't in the earlier linearizability, is this idea that when I go from a state to another state, this may not be a prefix, it may just be a subsequence. Okay, so there is a, it's the sense in which, so the -0 here is not happening after, but we are putting it before because it happened concurrently. Okay, and we see that a little bit here. So let's go back to here. This is a state which has a +0. We permit we permit an accessor which denies the existence of 0, and that's okay. And the reason it's okay is because the place where we would put the x0 is before the +0. Okay, so it gives us it increases the number of permitted behaviors in this distributed system. That's what we are doing. Okay, yeah. So that's the sense in which we are liberalizing the notion of time. We are now these edges are not about prefixes, but about subsequences. Okay, and the next thing we will do, and this is the last bit we need to do, is that the linearizability automaton is just insensitive to independence. Right? So what do I mean by that? Well, let's think of the binary set. The two values are independent. So what does that mean? That means a trace for a binary set really is two totally decoupled traces when you project down to the 0 bit and when you project down to the 1 bit. Okay? So in that sense, it's a little bit of this Mazurkiewicz independence there. Now what we're going to do here is this is a thing we are adding to specifications. We're going to enrich them with a notion of conflict. It's just a binary relation, yeah. And so for set, what is the binary? What is this conflict? Is basically the zeros are in conflict with each other, the ones are in conflict with each other, but the zeros and ones are not in conflict. We have a similar notion for text editors. Okay. Now why does this help us? It helps us, so let me just illustrate that with this example. So this was our example, okay? This was a valid execution for us, okay? Now what I'm going to do is, I'm only going to keep the order which comes from conflicting actions, okay? So here, 0 and 1 are not in conflict, so I drop that order, okay? And 1 and 0 are not in conflict, so I'm going to drop that order. Yeah? So basically the thing I've built here is the restriction of the order I see there, but to conflicting actions. Okay? And you see what do you gain from here? What you gain from here is now you look at that, you say, oh, I see why it's a set. And why is that? Because now you can see, so let's pick the 1. You see there's a 1 and a -1. And there's a 1 here which is not ordered with respect to those. So I'm allowed to do that. Similarly, there is the 0 and the 0. And the 0 is not ordered, so I'm allowed to do that. Okay, so throwing out the order between independent actions shows me this, allows me to identify the spec traces which it validates. Okay, and the same is true even with distributed text editor. Okay, now the net result of all of that is basically now if you think about so this is a portion of the the automaton I'm building. Between 0 and 1, well, of course, it's a product in this case, okay? It's the product between 0 and, the restrictions to 0 and 1. Basically, I have adding 0 and adding 1, and I built up the product. That is happening because in the case of set, it's a pure independence relation. And in other cases, it's not going to be. It'll be, the automaton will look different, but it's still, one can build it. Okay? So what is the idea? So this is the correctness criteria. I have not defined sigma for you, but I've told you what goes into building sigma. Let's remember, sigma is built purely from the spec. You give me a spec with a notion of conflict, I'll build you a sigma. And intuitively what sigma does is it incorporates these things. And what is the correctness criterion? The correctness criterion is that an implementation is valid exactly when the implementation is simulated by this automaton, okay? So now what can go, okay, let me tell you the results, well, what we can do. I can give you a different characterization, more direct, maybe in the tradition you're more familiar with. It satisfies the constraints I told you about. It's sensible for, that is, what does that mean? That means if an implementation satisfies the definition I've been trying to sketch, it will automatically satisfy these properties. Okay? It addresses all the CRDT examples in the literature. Okay? It satisfies the composition axioms, both in the sort of the horizontal sense and in the vertical sense. Okay? Since we're at Berkeley, I should pay a little tribute to some research which was done here, and I'll stop here. So let's look at a specific class of clients. Okay? So these are called COM clients, and the idea here is consistency as logical monotonicity. Okay, so what does that mean? That means, so let's look at data log programs. Okay, so that is Prolog programs without function symbols, and this is just a program to compute transitive closure. I just have these extra decorations just to indicate at what node these tuples are stored. Otherwise, it's just a data log, right? So, the idea in this family of languages is that, given such a program, it implies a distributed algorithm. So here, you take all these tuples, ship them over there, and, to add to the tuples over there, okay? And this computation requires no coordination, okay? Every node is running by itself. So the only place where things become non-monotonic in their sense is where you have state change, right? So if I want to go, for example, from state 0 to state 1, and how do we do these changes in a logic programming style? We do this with some notion of time. Okay, so at the 0th notion of time, we have a state. At the next notion of time, we have a different state. Okay, and this requires, in general, global barriers. Okay, but now returning back to the framework we are thinking about. So if we think of monotone clients, intuitively what is happening is there's no race between the mutators and accessors. And the work in the Hellerstein group has basically shown that a lot of interesting distributed protocols fall into this category. And for this category of clients, any system which is correct in our sense can be thought of totally sequentially. That is, you can forget all the distribution, forget all the concurrency. It's just you really can think of it as a purely sequential. So if you have a distributed set used by a COM client, the COM client can pretend it's a sequential set. Okay, so as a, right? No, that's, thank you for your attention.
We have time for questions. Yes.
In concurrent constraint programming, you have this notion of atomicity and eventuality. Can be implemented as a particular type system, constraint system in your case?
Oh, I see. So I think so I think the way I view it is that all the pure concurrent constraint programming in the eventual sense, I think it so I think it falls into this category of of these COM programs. Okay. On the other hand, if you are thinking of constraint programming with atomic tells, or you're thinking of constraint programming where you're actually changing state, it becomes non-monotonic. Okay, so I think the definitions I'm giving you apply to both, but in the case of eventual tells, they are they're quite powerful basically.
So in one of the first papers you mentioned, the one by Coherence, so they prove that linearizability coincides with
operational refinement.
Yeah.
Yep.
So what are you proposing? Is it then breaking what
No, so the paper which, so what O'Hearn and, the O'Hearn paper you're talking about, I can't find it. So they show that linearizability coincides with operational refinement when you have a concurrent operational semantics. What we are searching for is an analogous theorem for a distributed operational semantics. Okay? And what do we have? We have one direction of it, which is that correctness in my sense implies operational refinement for a distributed setting. So the sort of the statement of the theorem stays the same, but the context has changed. We have moved from concurrent to distributed. Okay, that's the difference.
So how does this relate to lattice variables or CRDTs?
So we are searching for a sort of a. So first, okay, concretely. All the example CRDT algorithms out there, they are all correct in my sense, okay? So I'm just giving you a definition, okay? So that's the first thing. But I think there's okay, so that's the superficial answer. I think the real, I think in a certain sense, the definitions I've described for you, I think they capture the semantic essence of what it means to be a CRDT, okay? So the way you are thinking, the way CRDTs are usually presented, is syntactic. They tell you here are the operations, and what you have to give me is what are the operations which are concurrent and what are the operations which conflict. If they conflict, how do you resolve them? And I think I'm giving you the style I'm giving you here. I think is because it's less syntactic. I think it has the possibility of capturing more things in that framework. Okay. But if you're thinking purely just CRDTs, I think even from that perspective, I think some of the properties which I've shown you are not as well known as they might be. Okay.
Thank you. I also have a question. Are there any protocols used, for example, in shared memory multi-CPU architectures that people have considered and that have only partial consistency, sort of more relaxed consistency, that in fact your semantics would not validate?
So okay, so just to sort of be careful, I did all of this for really distributed, not shared memory.
Okay. But
okay. No, I understand. No, I just want to be careful about. So I don't know offhand, but I'm sure there are. Okay, so I'm sure there are protocols. I was just trying to think of something, but because I'm certain that there are shared memory protocols which are not.
People have proposed all kinds of crazy things.
Yeah. No, because
it might be useful to apply these tools to analyzing them.
No, I agree. It's just so the reason. So we were thinking about it from a distributed end, and there are fewer constraints on execution at the distributed end. So that's why anyway. So I'm sure there are shared memory protocols. Yeah. Right.
All right. So thank you again.